I know, I'm so glad. I'm so glad it's getting cooler out. I hate summers in Atlanta, man. It's so miserable. It's like looking outside and sweating, thinking about going out there. It's just like, oh, so hot and humid. Can't wait till it's real cool. Did they fix the bulb? Yeah, so it's a little bit better. Alrighty. So, let's see. You'll notice that I don't have your grades back to you yet for your first assignment, but I have put up another assignment. So those are my priorities. Giving more work as opposed to returning work. So we have a few questions from, you're going to need your book because a lot of them had like little charts and stuff, so I didn't put the charts in. But the first, chapter 5, there's just a couple questions because they're pretty, they're a little more involved. You have to calculate stuff as to where like all the different jobs go and things. So on the first part here, I give you a recommendation as to how you can submit the answer for the Gantt chart, because it's asking you to draw a chart, a Gantt chart like we saw, where it orders all the different processes and how long they take. But since you're doing it in HTML, the easiest thing to do is just put down the process name and then how long it's running for, followed by the next process, how long it's running. Then I'll convert it back to a chart in my head. So I recommend, if you need the chart, you can draw it out and then just transcribe it into HTML. Now I also put up a tip here that when you are about to submit it, so when you're in this form, switch HTML Creator on. That will load this Java applet, and then paste into it. Because when you paste into it, when this is not on, it might look good on your submission, but when it finally submits, all the line feeds are taken out because it's treating it as HTML. So I can read it, and it's just easier for me to organize if you do this, because then all the line feeds between your paragraphs will show up. You don't have to do any of the other formatting. You can if you wish, like if you need bullets or anything like that. So this is a fairly interesting question. It gives you a list of processes and has you run some of the algorithms on it. Okay, so you can really see kind of how they work. This 5.7 is looking at two instances of time slicing, of using sections of time and slicing between them, and it has you do two different sizes of slices. I found this question was very, very good because it really it talks a little more, gives you an example of some of what we're talking about when it comes to why is it these IO-bound processes we want short time slices, why is it in the CPU-bound processes we want long ones. So it touches on all the major details of that, like the overhead of time slicing, how often something is going to go to I/O, and how long I/O takes. So that's another good example. So there's just two for that chapter since they're kind of involved. And then these are just content questions. They're just 4 kind of shorter answer questions. You don't have to go into too much detail. But they really talk about some of the different issues that we've already talked about some of them, but we'll talk about some of the others in more detail today when we get into some specific ways of doing synchronization. So I don't know. They touch on good content areas. Those 4 questions. These you don't have to write as much text on. Just pretty much answer the questions pretty directly. And then these will take you a little bit of time because they involve calculating times and stuff like that. Okay, so I tried to make it about the same length as the last assignment. The last assignment was probably a little more straightforward questions, but I wanted you to write a little bit more on them. This one, some of the questions are a little more involved, but you don't really have to get into too much detail. The questions are good enough here that if you just answer them, I know you've you've at least grasped some of what it's asking about. Okay? Yeah. Yeah, due Tuesday. On the discussion board, I've also put up, even though I have not returned the assignments, I put up my answers for the first assignment. So kind of what I was looking for. So you can take a look at that. And what I'm going to do is, since on the first assignment, I'm going to be fairly lenient on how I'm grading them, since it's your first assignment and everything. I'll probably just take off half a point or a point or so, depending on how close you are to some of these. And then also, when I'm grading assignments, I do take into account, like, if I didn't emphasize something a lot in lecture and it's part of the answer, I won't really count off for you not having, that much, you not bringing that particular aspect up. So what I brought up yesterday or Tuesday about the economics of time sharing and stuff like that, if you don't have that aspect to the answer, I'm not going to count off for that. Okay? So you can take a look at those things. Also in the discussion board, there's still the project topic section. If you guys, again, want to start tossing around ideas of what you want to do your projects on, post them up here. One, so I can respond and give you some more information as to whether I think it's a good topic, but also so that it's out in the open, so that others can benefit from seeing how I respond to your topic idea. It'll give them a better idea of what they should propose for their projects. Okay. So last week, or last class, Tuesday, okay, we were talking about synchronization. And slides. Okay, we had one very, very interesting algorithm that we looked at for synchronization, and that was the Pellicer solution. Okay, and it's just a few lines, but we found out that looking at these few lines ended up being fairly complicated because we had two processes running at the same time. Okay, so what I asked you to look at before we ended class was looking at this Pellicer solution and looking at our initial problem, our initial example problem of the producer-consumer problem. Okay? When we walked through producer-consumer, broke it down into individual machine instructions that we'd run, right? And then saw that, well, if a particular order of these instructions happen, we'll have an inconsistent state, which is bad. Okay? Then we introduced the Pellicer solution, this fairly short little piece of code, and I asked you, how does this solve our producer-consumer problem? So, first of all, does everybody remember race condition from producer-consumer? Okay, so everyone remembers how that worked and why we had a problem. Questions on the basic Pellicer algorithm? In the Pellicer algorithm, we have two flags and then one turn. Okay, the flags say ready, whether a process is ready, and turn says whose turn it is. Okay, so last time we walked through it by having the variables and then walking through both sides. Okay, we're only going to go through the interesting scenario. Okay, where they both kind of get to the same point. So we'll have flag 0. What does flag 0 equals false mean? What's that? Which process? Process 0. Okay, we'll just number the process 0 and process 1. So process 0, not ready. Flag 1. Process 1 is not ready. Turn 0 means, what's that? No, it doesn't mean it's somebody's turn. Whose turn? Zero's turn, right? Process 0's turn. We can initialize this to either. Okay? So, this is the state of the flags. Remember, these flags are shared between the two processes. Okay, that's how this whole thing is working. Okay? So, these are shared between the two processes. Now, we start running. Okay? We'll start running in process 0 first. Okay? Process 0 comes through. The first thing it does is okay, which flag does it set to true? It's I is the index. So I means who? 0. Means the process that's running. Okay, because when I go over there, I is gonna be 1, and J is gonna be 0. Okay? So for right now, process 0 is running. Flag I equals true means flag 0 equals true. Okay? Turn equals J. So we're still in process 0. What happens? Turn becomes 1. Because J means other, right? The other process. Okay, so now we'll context switch. Okay? Well, actually, let's not context switch yet. Oh, no, we do have to. We're going to context switch now. Okay, so process 0 stops. All its state is saved. Then we switch to process 1. Okay? Its state gets loaded. And where is it in the program right now? It's at the beginning. We haven't done any instructions for process 1 yet, right? So, process 1 comes through. Now what does flag I equals true mean? Flag 1 equals true. Okay? Let's make it interesting. We'll context switch again. Okay? So we're context switching again before turn equals J. So we switch back to process 0. Where was process 0 when we switched? Right before the while, right? It was about to enter the while loop. Now it does enter the while loop. What does this value equal? What's flag J? Flag 1. And what is that? True. This condition is true. So we move on to look at the next condition. Turn equals J. Turn equals, so does turn equal 1? Yes. Both conditions are true. What do? We loop, right? Because there's an empty while loop there. So we loop, and we continue to loop as long as those conditions are true. So I loop, and I go and check them again. Is it still true? Yes. I loop again. Is it still true? Yes, and it will continue to be true because we're not altering the values. So what happens? A context switch happens again. I'm process 1 again. What statement's next for me? Turn equals J. What is J in this case? 0. I say turn equals 0 because J is the other process. So if I'm process 1, J is 0. If I'm process 0, J is 1. I and J mean I means me, J means them. Okay? Turn equals J. So turn equals 0. Right? I go to the next statement. Flag J. Flag 0, is that true? Yes. Turn equals 0. Is that true? Yes. So what do? I loop. I loop. I loop. What happens? Context switch. Here I am again. Process 0. I'm still executing the while loop. So now when I execute the while, when I evaluate the while loop, flag J is now what? J equals 1, right? Because we're 0, other is 1. Flag 1 equals true. Turn equals, we actually evaluated it wrong on the process side, but turn equals what? Turn equals J. Oh no, actually we did it right. What's J? J is 1. Does turn equal 1? No. Right? Turn equals 0. It does not equal 1. What happens when one of the while conditions is false? We break out of the while loop, right? We continue past the while loop. So as process 0, what do? Critical section, right? I start entering this code and I run code. Okay? I can task switch as much as I want while I'm running this, right? Because if I task switch, what is process 1 still doing? Still looping, right? Because flag 0, still true. Turn equals 0, still true. I switch back. I continue through my critical section until, so flag I, if I'm process 0, what am I referring to when I say flag I? Flag 0. That becomes false. Then I can run some more code. Okay? If I context switch, right? I'm still here. Flag J, if I'm process 1, flag J is referring to flag 0. Is flag 0 true? No, it's false. This is false. What do? Continue through the critical section. Okay? The key there, only one of us were running the critical section at a time. That's the algorithm. Okay? Now, how does this solve our problem that we had with producer-consumer? Okay? So, it helps us with, the problem in producer-consumer was we both tried to update the counter. So, what do? How do we do that now? So what do I do with counter plus plus and counter minus minus? Where do I put them? I need to put access to counter in the critical section. Whether it's plus plus or minus minus, we'll have different critical sections, right? But by doing counter plus plus in here, or counter minus minus in here, what does that do to this?
Puts all the blues together and all the black.
Okay, that's black. I think it's red.
Yeah.
Okay, so all the black statements, right? These, they get together. These blue statements, they get together. Which one's first? We don't know. No matter which, whether we make one process 0 and one process, it doesn't matter. It all depends on when context switch happens. Okay? So, these two go together. I mean, these three go together, these three go together. Who knows which will happen first? Okay? Why does this solve the problem?
Just guarantee that only
Okay.
which means that only one, the counter can only be updated.
Well, here the counter could only be updated one at a time too. Right? No matter what we do, we cannot run count equals register 2 and count equals register 1 at the same time. It's impossible if we're on the same processor. Okay? Only one of them we're updating count here as well. How did we solve the problem? What was the problem?
You have two different values in
In
the registers.
the registers, we had two different views of counter, right? We kind of had an old value of counter in both registers, right? And then we update them, and then we go to store them back. We have two different answers, okay? Now, what makes the algorithm, the Peterson algorithm, so special? It's still dealing with the same problem. We have two processes running. We're even updating more values here, right? How did we solve the problem? What is different about this update to counter compared to these updates that we're doing?
You can't update it without saving.
What's that?
You can't update the counter without saving it to
I mean, saving it back to
the
memory,
variable,
right, to the variable. Okay, so that's one aspect, is we're writing something back to a variable, right? Turn is a variable. Both of us can write a value to turn. What, can we just replace turn with counter? I mean, by that logic, right? If this updates turn correctly, the other set of code didn't update counter correctly, why don't I just make turn the counter? What's the difference? We need to make this set of three. What do we need to make them? What's the term? We need to make them atomic. Right? Why? We want it all to happen without interruption. Okay? What do you notice about these three? They're getting a value from count, modifying the value, and writing back to count. What do you notice here with turn? They're writing a value to turn. Do they care what turn's value is? Right. Well, I mean, but at the time of writing, do they care what the previous value was? Do they care if they're writing the same value that it already is? They don't care anything about it. They're just writing. Okay? The key here is that that's an atomic operation. Okay? No matter how you implement it in hardware, if you're writing to a memory spot, right? Process 0 might go first, process 1 might go first, who knows? They might end up writing in a different order than when they started the instruction. The key here is that when they're done, only one value will be in turn. Right? We don't care which value is in turn. Okay? It could be 0 or it could be 1. We're not basing it on any previous information. We're not basing it on any instructions that happened before. It's atomic. Okay? So no matter which value ends up getting written to turn, somebody will get to break out of the loop. Okay? In other words, what we've done is that we've taken this more simple instruction, this atomic instruction, and extended it out to make more complex instructions atomic. Okay? No matter how you juggle the instructions around between process 0, process 1, this value will only be one value when you get to it. Okay? So you could probably create something where these where you can change fast enough between the flags, but you keep everything as atomic as possible, extend it out into something that we know. We have an example of how its instructions getting out of order will break the operation. Break it to the point that you get values, the incorrect values. Okay? So, this idea, being able to have this primitive action that we can do to ensure mutual exclusion for a critical section, this is how we do synchronization on operating systems. Okay? Does everybody see the difference between just assigning J to turn and loading count and then assigning a new value to count? Okay? Because our inconsistency comes from the fact that we've manipulated the previous value and we're storing the value again here. Okay? This is one example of how breaking up instructions can mess up your results. There's plenty of others, and they're not necessarily in this order. Okay? The key is, though, that algorithms such as this can ensure that we can extend that atomicity to arbitrarily large sets of instructions. Questions?
So in terms of registers, how is turn equal J?
It's probably, well, J is essentially going to be a constant in some way, but that can still be a variable. We can load it into register, right? And the key here, though, is that J is not the same location turn is. J is always going to be the same value. So we can load J, same thing as here. Okay, register 1 equals J, right? No statement here. Turn equals J, or turn equals register 1. Okay, the key is that it's kind of a read-only of the previous value and then, okay? So even though we can load J into register 1 and then have an interrupt, in other words, have a context switch, nothing that the other program can do will affect our view of the system when we come back. If you make it so that the other process can manipulate J in some way and that impacts, whatever happens with the turn, you haven't done the algorithm right, because now you don't have atomicity for that operation. But in instructions, it would be register 1 equals J, and then turn equals register 1. Any other questions? Those of you who weren't here on Tuesday, I'm surprised you don't have questions, unless you have a lot of experience with multi-programming. I hope that after today, you're going to go back and furiously study this on your own so that you do actually get it, as opposed to right now where I think there are probably plenty of questions that you don't want to ask because you weren't here on Tuesday. It may be helpful to ask them now because we can discuss them. Maybe some of the other people who have been studiously coming to class will benefit from it, but I hope that you either get it or will study furiously.
Actually get lost just when you beginning, flag 0 with the control.
What's that, the term, flag
The
0?
first flag 0. From that point,
Oh,
I
at
get
the beginning?
lost. At the beginning, when it is first place is false, then when flag 0 become true, and then context switch. From that point, I just
So the first
it just
context
went out.
switch.
Yeah, I just can't control anymore.
The thing is just,
I just need more backup for this one. We need more backup. So I mean, to just get on the red light, see that. I mean, that one I don't see no more.
don't think. I mean, don't try and, the key to making this work is not to look ahead at all. Don't look ahead, don't think about what the other process is going to do, is you need to mechanically just walk through and think. Just walk through it, and if it stops running that process, you stop running the process. Don't look ahead, don't worry about the meaning of the flags, don't worry about the meaning of the terms, okay? You need to mechanically walk through. Now, as far as deciding when looking at this algorithm, when you want a context switch, I can't really tell you when good times to context switch are, but try it in between. The key is try it between two important instructions, okay? Because if anything is going to go wrong, it's going to go between, for example, setting a flag, setting term, and that kind of thing. Now, if you're having problems visualizing running multiple processes, you have to understand that a process running is nothing more than the next instruction and the state of the variables. So as long as you write down the variables and you keep your finger for each process what the next instruction is, you should be able to walk through it, okay? Because as long as you don't let any outside understanding of the rest of the instructions come into play, that's how the computer does it, is it walks through instructions and then looks at the state, okay, looks at the variables. Okay, so what do you think is unclear as far as when walking through?
When you erase them and write it, then I get confused. It's better if you write it out.
Oh, step by step?
Erase it and write it, and that's what makes me confused.
I guess the reason I'm erasing and then writing there.
Like step by step, writing first, then I'll be able to understand.
Okay, we'll do one quick run through with that. Okay? But now keep in mind there'll be, since we're running two processes, there's a lot of time steps, okay? Because we're running kind of two timelines. Okay? At time 0. F0 is, I'm just going to do F0, F1, and T. Okay? F0, false. F1, false. T, 0.
What is that?
Flags, 0 and 1. Okay? What's the active process right now? We'll start with process 0. So I'm going to put process 0. Okay? Process 0, flag 0 is 0, flag 1 is 0, turn is 0. 1. We're at time step 1, we've gone through the first instruction. So we've set flag 0 to true. Okay? Everybody understand my notation? State, process that's running. Okay? Time. Okay? Step 2. We've run the second instruction. What have we set turn to? 1. This doesn't change. This doesn't change. Okay? What are we going to do? We're going to context switch.
That,
Yeah.
why are you gonna have this part?
Because that will break it. Okay? We've already run through, if I just let process 0 run all the way through, and then let process 1 run all the way through, nothing interesting happens. Right? If we let process 0 continue here, flag J would be false. Right? Flag 1 is false. So what would happen? It would continue past a while, run the critical section, right? Run the next piece, and then we context switch, and then process 1 would do the same thing. Okay? The reason I'm context switching here is because we already saw what happens when that happens. Remember, we went through this on Tuesday. We ran right through.
And my point is that how the practice is controlled here in the program.
By the operating system. The program does not have any idea when it's going to be context switch. Okay? In fact, even if we had an idea of when it would context switch, we can't guarantee it. What if other processes come in? What if, I don't know, what if we get reprioritized in the schedule? Okay? The key here is that this algorithm can handle context switching anywhere. Anywhere in the code, between any of the processes, you can context switch. That's the key. That's why we're doing it. Is we need to be able to handle any context switch. So, context switch. What process is running now? P1. Okay? It runs the first statement. Does it modify F0? No. F0 remains 1. F1, what is F1 now? True. Does it modify T? T remains 1. Next step. Next step, turn equals 0, right? So we set T to 0, okay? These go unchanged. We can only do one thing per instruction, so we do it, okay? Time step 5. Do we modify any variables? Where are we? What's time step 5?
Right there.
Do we modify any variables in this statement? Is there any modification of variables? No. So, evaluate the statement. It does not. Okay? Flag J is what?
1.
Flag, what is J?
J is
Is 0. Because we're in 1. So J means the other. F0 equals true. J equals 0, right? Does turn equal 0? Yes, both are true. We do not go into the critical section. What do? We loop. Do these change? No. Have the conditions changed? No. What do? We loop. I can continue writing steps for looping as many times as I want. We have no statement that changes any of these variables. The state will never change. We loop forever until context switch. We need to get to something that can modify these variables. Okay? we know that right now, okay, at this point, we know process 1 cannot continue until the variables change, right? In this state, it cannot get past the while loop. Where were we with process 0? Well, we went through one statement, two statements. So we were done with turn equals j. So we're at the while loop. Is there anything in that statement that can modify a variable? No. So we copy down our state. Evaluate it. What is j now? It's 1, the other, right? So F1, is that true? Yes. Okay? If j is 1, does turn equal 1? Alright, when I say does turn equal 1, you look here. Don't look at any other code. If I ask you, does turn equal 1? You look here and you say no. Right? Because that number is not the number 1. Right? So turn does not equal 1. False. What do we do when we're false? We break out of a while loop. So, we continue. And we continue as long as we want. Does anything in this critical section modify flag 0, flag 1, or turn? Anything in this critical section? This part. It cannot. The critical section cannot touch those variables. If the critical section cannot touch those variables, what do we know about process 1? It cannot continue. We've already established that, right? If the state doesn't change, this cannot change, right? Until the state does change. Where's the first place the state can change? Right here. How does the state change? What is I? If I'm process 0, I is 0. Flag I. Flag 0 equals false. F0. False. Do I change this? Do I change this? Okay. We're still running, right? But we do know one thing. The state has changed. There's a possibility that this could affect process 1. Let's see how it does. Context switch.
Actually, wait until we get off that curly brace or that part, even though the state is changed.
We might. We don't know.
So the process 1, process 1 is going to be waiting until that, right? Or it could be.
Process 1 can't do anything until we switch to it. Right? If it's not on the CPU, it can't do anything. Do I need to have this line here and switch to process 1? No. We can continue running. That's fine.
On the operating system.
Right. Okay? Where I'm switching is arbitrary. I'm switching at points where interesting things are happening. Okay? You should run through these where nothing interesting happens so you can see what happens in normal operation. Okay? So if I were to switch there, the state has changed. The while loop doesn't do anything to change the state. So if you're process 1 and you look at this, you look at that. If I'm process 1, what is J? 0, right? Is F0 true? Is F0 true? Where are you looking? Here, not up there, just here. Just the state, and only the state can determine this, right? Is F0 true? No, immediately. Done. While, break out, start running critical section. Okay? Now, again, why you're context switching? Completely arbitrary. It's up to the operating system. The key is, like I said before, the code needs to work no matter when context switches happen. It needs to work if there are no context switches. It needs to work if there's a context switch after every statement. Okay? And all combinations of statements in between. Okay? That's the key to this, is making sure that we have this lock on when you can progress and when the state can change. And we need to make sure that those two things can't happen inconsistently or non-deterministically. Questions? Okay? But when doing these exercises, especially when you get into multiple processes, okay? How many of you have taken automata already? What's that? Oh, I don't know. How about PLC? PLC. How many of you are familiar with Turing machines? No? Okay. That would help. No, but the key to thinking about computers are these two concepts. You have state. State is variables. Okay? You need to think of these processes running as the program is what you do when the program is how you go from one state to another. Okay? All your variables are the state. Okay? To a program, to a computer, those are the only two things that matter. What your next instruction is, what the state is. Okay? So whenever you do it, look at the instruction, right? It's evaluate flag I and turn J or whatever. Okay? So that's your instruction. Okay? Stop looking at the program. Stop looking at it. You don't care what the next instruction is, whatever. All you know is I need to look at these two different variables. Go to your state, your list of variables, and say, what is the state of those variables, right? True or false or whatever. Come back and you say, okay, the answer to that is true or false. Then you decide what to do next, okay? So just concentrate. The next instruction, your state. Everything else, don't look ahead. Don't worry about when a context switch is happening. Don't worry about which process is running. Just next instruction and state. Okay. Questions? I'm not going to walk through it again.
No, I know. I understand. My question is like, probably it's a stupid question. What happens if there's no interruption?
We already ran through it. Nothing happens. Right?
It's a process.
The state changes and everything, but you just walk through the instructions. And then the other process walks through the instructions. Okay? And what we're seeing here, this is kind of, these are the critical task switch. Okay? We can do additional ones. If you add in ones here, not much changes.
We haven't really identified how to know the section is critical, right?
Well,
Is that kind of arbitrary?
it's not arbitrary, but there's no easy way to say whether something's critical or not. You really have to look at, we're going to see some of the classical problems, and you'll see that it even matters if you're just reading the variable or if you're writing the variable. There's different classes. Now, it's not a straightforward way to know if something's critical or not. That's the voodoo behind multi-threaded programming. The idea is that there are plenty of programs that are written incorrectly as far as this goes out there, and no one knows because they haven't gotten into a particular situation where the race happens and something goes wrong. Okay, but there's no like really automatic way to find out. There's really just rules of thumb, kind of design patterns that you see, and when in doubt, lock. You know, if you're not if you're not 100% sure as to whether or not something can race and clobber each other's data, lock. So,
Say lock, you mean
this.
set it up, so.
Make it critical. Okay? Why don't we just lock everything? Where are we wasting time? The while loop, right? One of our processes is sitting there doing nothing. Okay? And we'll see there are multiple ways to make a process do nothing. Some of them involve putting the process to sleep and having it wake up using an interrupt. Okay? But some of it is exactly like this, where it goes in a while loop. That's called a spin lock. Okay? It's called a spin lock because one of the processes is spinning while the other one's running. In other words, going through a useless loop. Okay? It actually has some benefit. But the idea is that if you lock everything, every time you lock a section of code, you're saying multiple things can't happen in the operating system. And we've already determined that having multiple processes able to run at the same time is desirable in an operating system. Okay? So all of synchronization is a push and pull between safely running code so that it works in a way that's the same every time and getting performance that we get from doing multiple processes. Okay? So, other ways to make things atomic, really, okay? Other ways to get this non-interrupted atomicity. Is there a single sign language for atomicity? Atomic? Really? Sorry about that, but it's a critical vocabulary word. Hardware synchronization. Okay? What we saw here is a kind of software algorithmic way of providing synchronization. Okay? What is the key attribute of this algorithm? What did it provide to us? It provided locking. In other words, the critical section becomes atomic. Okay? So atomic means it's not going to get interrupted. What's another way to make it not get interrupted? Don't interrupt it, right? That's another way to do it. Is if you don't want a process to get interrupted while it's running, don't interrupt it. Okay? Simple enough. So what do? In hardware, we say, turn off interrupts, run this section of code. When you're done with the code, start interrupts again. Do we have to worry about our producer-consumer problem? Problem here? These didn't run together. Okay? If I turn off interrupts here, and I run this instruction, and I run this instruction, can we interrupt it and switch to the other process? No, there's no interrupts, right? No interrupts available. So what will happen? We'll continue running, so this will get up here. Then we can turn interrupts back on. Okay? So one way to not get this problem, don't interrupt a process that's doing something critical. Okay? So instead of putting a critical section here, you put turn off interrupts, turn on interrupts. And you accomplish the same thing. Now, what's the problem? Right, and then what will happen? Your computer cannot do anything else. Right? Why can't the operating system solve that problem? Because you can't interrupt it, right? When an operating system puts a program on the CPU, operating system is dead at that point, right? The operating system doesn't exist anymore, right? The CPU is all that exists, right? That's what's running. If you put something on there, the only way to get the CPU back from the process that's running is a hardware interrupt, a timer. There's no other way. That's it, giving it back, right? So, it can give it back, but the only way to take it back is a hardware interrupt. You disable all interrupts, broken, right? Okay, so the idea is you want to not turn off interrupts as much as possible, okay? Now, the other thing is, okay, is this only works on uniprocessors. In other words, on multiprocessing machines, you can't really disable interrupts. Unless, well, I mean, if you disable interrupts on a processor to make sure that that process is running, that doesn't change the fact that another process is running and could be manipulating the state. Okay? Your only choice in a multiprocessor operating system would be to disable interrupts on that one processor and stop the other processor, right? Because the key to all of this is you do not want the state of the machine to change while you're running, because you need exclusive access to changing the state. Okay, so that's why in general on multiprocessor machines they're going to use locking. That is what I said before, spin locking, where you'll let another process run in this loop to kind of keep it stopped, right? And in uniprocessor machines, though, you have the option of maybe disabling interrupts for critical sections, okay? And the other thing is you do not want to give users who write programs on your operating system, you do not want to give them the ability to turn off interrupts, okay? It's always desirable for a user to turn off interrupts, right? If they can get exclusive access to the CPU, they'll take it. So you do not give them that access. So this is usually reserved for kernel operations written by the operating system. Okay? And then the other option for providing some of this capability is provide more complex atomic instructions. Okay? What I mean by that is, for example, with the counter, if we could load a value from memory, increment it or decrement it, and then save it back to memory, if we can make that atomic, we no longer have a critical section problem, right? In other words, if we can make one instruction that does all three of those steps that we saw in the individual pieces of code, we don't have an atomicity problem, right? Because if we run that instruction, it will run without interrupt, and then the next one will come and it could run the same type of instruction. And we never get in that case where it's half complete and then the other one starts and writes different values. So that's another solution. And usually more complex processors will provide some higher level atomic operations. Okay? So before we get into those, let's take a 5-minute break. Absorb some of the multiprocessing. I haven't returned it. I posted up the.
Yeah, I have a question. Like, I don't know if you noticed or not. We got this is the first time I used the city for the homework, and I thought I'd turn it in on the 10th day, but my friend, I checked the next day that I'm turning in, so that's why my.
Oh, that's all right. On the first one, I'm gonna be pretty
But I just
lenient.
want to let you know because that was the first time I would use Web City for the homework.
No problem. No problem.
Process is going on.
Okay.
Should have done it on the first day.
All right.
There's a lag time when you're speaking
Okay.
She's getting the message like 5 seconds behind everybody else.
Okay,
And when you're pointing on the computer and saying here, 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 she's watching us.
right.
She can't see what here is, and all we're doing is saying here. So she has no clue what here
Okay.
is. So if you could maybe verbalize it or.
All right, to what I'm pointing to.
Right.
That kind of thing. Okay, no problem.
You can email the slides.
What's that?
The slides. Can you email them?
So that you can get them outside of
I
WebCT?
kind of want to print them 6 to a page.
Oh, the original slides?
Yeah.
Oh, I don't have them. I think they're from the author.
Like when you display them. Maybe it's, I don't know how to change it.
Just single per page. I don't know.
Because it still has a big board, like the ones you printed, 2 per page.
Yeah,
It's still,
I think that's a function of Adobe.
I can change it there.
I think Acrobat should be able to rearrange slides into multiple per page.
I'll try it.
I'm not sure. But I don't have any kind of like original source of the slides, so, as far as putting more on a page. I'm sure Acrobat has something on that. You just have fewer pages not to be able to print. I think that'd be more efficient. What's the number on automata? Is automata required for undergrads?
No.
Automata? It's not required for undergrads?
Only grad level class.
It's 45.
No, it's 4.6.
45.
Really? I think they don't even offer no more. They offer graphic user features.
No, but it's 4.6. I mean, it's cross-listed.
Yeah.
It's not required for a catalog.
It's not required for undergrad,
Oh, that's no good.
but it is for credits.
Yeah.
I like that class.
Did I call you guys? Not even like last year.
It's a very hard class, and Adobe built it pretty much.
Oh, it's hard. I mean, that's no reason not to require it.
Right? It's like POC.
Right. Oh, now I'm gonna lament on the state of computer science today. Remember back when computer scientists were computer scientists.
That's about as abstract as it gets, though,
But and because it's so abstract, it's one of the most universally useful classes ever. I mean, the idea of, that will that solves PLC for you, compilers, stuff like this, operating system stuff, all of it solved. I mean, that's all you do. If you're a computer scientist, all you're doing is working on automata, Turing machines, and all that. So, if you can understand those, all this stuff has to work.
And the other thing is that Turing machines, we hardly spend any time on, like maybe the last 2 or 3 weeks.
Well, because at that level, it's a computer. Once you get to the level of Turing machine, you're so universally powerful that you might as well talk about it abstractly. But the basic stuff, like the basic, DFAs and stuff like that, that really gets you in that habit of looking at things as everything you do as state and transition.
Can we come to your office and talk about myself?
Sure. So I'll be there today. Tomorrow I'm not in the office. I mean, usually I'm in my office in the morning when I call. Mondays usually not, but I'll be there after class today. You said you were going to come by as well?
Yes.
Okay. Talk about project. So usually when I leave here, I will grab some lunch and then be up in the office. So, and then I'll usually be there all afternoon.
Actually, I'm
Okay, that's fine. That's fine.
regularly more, so I can talk about.
Okay, no problem. Okay, so we're going to briefly look at 2 of these kind of hardware-provided atomic operations. It's called test and set, okay, and the other one is a swap operation, okay. So what you'll see is, for example, with test and set, okay, you're test and setting a variable, okay. So what we'll do is we'll load the variable into basically like a register, right? We'll set the variable to something and we'll return what the old value was. Okay? So this can help us with some of these operations where we're getting a flag and then setting it to something else. Okay? It's a very useful atomic operation in that stuff like what we did in that Peterson's algorithm, okay, we can do with fewer statements because, again, if we can guarantee that it won't be interrupted, we don't have any of these synchronization problems that we saw, right? So the idea here is we see this as 3 lines of code, okay? But hardware that supports this concept, this instruction, would do it as 1 step. In other words, it will not interrupt in between these because we've already seen what happens when we walk through the algorithm that testing a value and writing a value that we can interrupt in between them and it provides different results depending on whether or not we were interrupted. Okay? So doing this is kind of like, think of any of these instructions as right before I execute the statements in the instruction, I turn off interrupts, execute this little instruction, and then turn them back on. Okay? That's not how it works because, again, this is hardware provided. In other words, if you were to look at the assembly, there's another opcode, right, for this test and set. That's different than loading a value from memory, comparing a value to a register or whatever. Okay? This is done as 1 instruction, no interruptions. Okay? The other one, this is kind of doing some of this stuff, kind of combining some of those steps of what we saw before, the same idea of you see if it's true and you attempt to lock it as well, all in 1 step. So only one of you will be able to grab that flag while it's false and keep it set true for the other guy. Right? And then you run your critical section and then you can eventually unlock it because you're done. Okay? The concept behind this is right before you go into your critical section, you turn the lock off, right? You say the section is locked by setting it. And at the exact same moment, you're checking to make sure it wasn't locked before you set it. The reason we can do it in this simplified form with just in the while loop doing test and set is that we don't get interrupted when we run it. Okay, it's kind of breaking out. If you were to break this out of that single instruction, it would look kind of like the Peterson algorithm. Okay, then you run through and then you can just do a regular lot here because you don't need to test it as well.
When we could test, how would you exactly like give us these questions? Like it's weird, lot, like theoretical questions.
Questions like this, I mean, this kind of stepping through is a big candidate.
Really?
Because I can do something like, suppose I'm interrupted here. What will happen? Okay? But some of the other theoretical questions are, do you see a problem where we can run into a race condition types of things? Okay? So like what we went over with the producer-consumer, showing how by interleaving those instructions, I might show you a set of instructions and say, explain the race condition here.
Would it be like our homework at all?
Some of it will be like the homework. This one has some theoretical questions on things like these atomic operations. But things where I spend so much time walking through them like this, I'm going to ask about that. I mean, there's no, right? I'm not sitting up here and going through, the steps just to, So I'm going to ask on that stuff because if we've gone over it a bunch of times, I expect you to have absorbed it in some way. And you've had an opportunity to say, hey, I didn't absorb it, right? So that we can go over it some more. So I'm definitely going to ask about those. And then, yes, I'm going to ask you about the content of your questions. Like, this stuff is going to be examples like this because that's how we've been describing the kind of theoretical concept. On the scheduling stuff, expect those to be like your homework questions, where I have you run through algorithms, okay? And all of these, I like to run through algorithms, and I like to see if you can find situations that are different from the way we ran through the algorithm in class. In other words, do I know you can step through the algorithm and run into these pieces and tell me what happens? In other words, you know what's going to happen when you run through it in the steps that I did. But if I give you a different set of criteria, can you still step through the algorithm? And again, maintain that focus, looking at the state, going to the next statements. Okay. Another thing that's often that has the option of being provided in hardware is the swap operation. Okay. We all know that you can't swap. You need 3 variables to swap, right? I mean, that's something that we run into in programming all the time. Okay, and this is the typical way of doing it. You load a value into a temp. You put you exchange one of them and then load the temp value into the other. Okay. This is again another obvious area where interleaving can really change the results, right? While this temp value is loaded up here, right? If we modify some of these values, we could lose data, right? If we're setting A to B, if something else modifies temp, or if we change the value of B at that moment, like we were changing the value of B, we might, when we start the operation, we want A and B to change places, okay? But since there's so many instructions that we're doing to switch A and B, the state of A and B when you begin the instruction and the state when you end could be different if somebody modified them. Does that make sense? In other words, the whole key to this synchronization idea is we want the state of everything to remain constant while we do the critical section, despite other processes wanting to change that state. Okay? So here, the beginning of the operation, A and B are this. When I walk through the statements, I want them reversed, but I want to make sure that the reverse values reflect what the original values were. Got it? So it's critical. Well, if we provide this in hardware, we can do that swap in one statement, and in fact, we may not, it also solves the other problem that we all know. You need an extra variable to swap 2 variables. Okay? So we provide this in hardware, it does it all automatically. The values of A and B were swapped, no interrupts, no temporary variable that we see.
Is that like the 2 XORs?
What's that?
To swap two variables, like two values, you only need like a hand and 2 XORs.
Probably, but you do need to hold one somewhere and do that. Are you talking about the gates that you need
Yeah.
here to do it?
It was, well, I don't remember. It was a project or an assignment we had to do in some class.
Yeah, I mean, in hardware, I don't know if you'd need, what's it called? Flip-flops to do it. You might need them. I don't know if you can. I did horrible in architecture, but
When you say in hardware, this needs to be done, I thought that might be what you were talking about.
sure. I mean, I don't know how they're doing it. They might implement the circuit you're thinking of. Or they can do it by just dropping it somewhere real quick and then swapping the values. But the idea is that when you're done, the two registers have swap values. Okay, and they show us an idea here with swapping lock and key. Okay, and they make it so that you can kind of, when you get past that while loop, in other words, you've entered, it atomically, right, in one step, make sure that you've locked it for the next person so that they have to wait at the while, right, and you get to proceed. Okay, so again, all of these are different variations of us testing and letting us go through a barrier and locking it for the person behind us. Okay, because the whole critical idea is you don't want two people to slip through the door at the same time. Because if you do that, you get into all this mess of them writing over each other's data. Okay, so all of these operations are different ways of doing that. Now, having said that, having showed you these two different test and set and swap, we're not really going to talk about it much. Having talked about you can disable interrupts before you enter the critical section and then re-enable interrupts, we're not going to talk about them, okay? Because those are all the different ways and mechanisms that we can do this synchronization. How we do it is up, the operating system makes decisions, the capabilities of your hardware makes those decisions. If your hardware doesn't have a swap operation, you don't get to use it, okay? If we're on uniprocessor, on a single processor, right, and if we're on uniprocessor, we have the option of turning off interrupts, right, and then turning them back on when we're done with our critical section, okay? I do not have the test and set operation on my chip. Can I do test and set? What's that? How do I do it via software? I can't just do this, right? I can't just do that as my software. Why? It's not atomic, right? If I get interrupted in between these instructions, bad things happen. So, can I do test and set? On my uniprocessor machine that does not have this instruction. How? Too much. You could. But chances are we're trying to do this so that we can implement Peterson's solution easier. What's the simple way to make sure that these instructions will happen atomically? Disable interrupts. Okay? We can do the same thing. We write this code, turn off interrupts, do these 3 steps, turn interrupts on. Now we have a very good primitive for doing other things, like simplifying the Peterson algorithm and doing this, right? So what we've done is we can give the programmer the idea of test and set, and when it comes down into our kernel where we're writing the code and we know we're not going to do bad things by disabling interrupts, we'll safely disable interrupts, run our test and set, re-enable interrupts, and then come back.
Does it interrupt this program?
we can interrupt wherever we want here, in any of the critical section or anything. The key is that this test and set will happen at once. In other words, no interrupts within test and set. Okay? Because if you look at this, right, and you get to this section of code, you actually do a function call. Right? And you function call to this, and then you start walking through these lines. Okay? No, that's the thing, is if we're the operating system implementing this, before this function call, we disable interrupts. So we say, no interrupts, run these lines, and then re-enable interrupts.
So are all these little algorithms, are they perfect? And then like, because if there's an interrupt, and if it fails, it's a block the machine, right?
Yeah, I mean, yeah, no, they work. By perfect, you mean they'll deterministically happen, yes. Because see, and the key is, a lot of the key of this are these ideas that when you get down to a level where you can atomically do something, right, do something without interrupt, you can guarantee this behavior. In the fact that, yes, both of these processes might be able to try and write to turn at the same time. Okay? But no matter what order it happens, only one value will be in turn by the time you look at it. Right? So that's how we guarantee it. So yes, if you can get it down to atomic, then yes, they do guarantee the behavior. Okay? Now, that doesn't mean that you still can't do the synchronization wrong, but the primitives that you're given work, like test and set and these kinds of things. Okay? So now, moving away from that, these individual instructions like test and set, synchronization and swap, okay, and even the Peterson algorithm. We move away from that, and we try and all of that was to say, look, we have ways to make critical sections, right? Okay. So knowing that we can do those basic things, we try to get more complex synchronization primitives so that we can do more complex things, like use of a semaphore, okay? Synchronization tool that does not require busy waiting. What is busy waiting? Spinning, right? What's spinning? Going through this empty while loop while you're waiting for the flags to change. Okay? So, semaphore is an integer variable. Okay, the semaphore is it's a type of variable. It's a variable that's special in that we have operations to access it atomically. Okay? Now, this special integer variable, two operations must be provided for it to be a semaphore. Okay? Wait and signal. Okay? In traditional books, you'll see them as P and V. I think it's because of like what wait and signal start with in Dutch or something, but we'll usually see it as wait and signal. Okay? Notice here, can only be accessed via two atomic operations, right? Two indivisible operations. We have wait and signal. Okay? What is signal doing? Incrementing the semaphore. What is wait doing? Well, it's waiting for the signal to get above 0. Once it's above 0, it will decrement it. Okay? This is kind of like what we saw before, but before we were binary. We were saying, when it's our turn and the flag's there, we can go. Otherwise, we have to wait. Here it's we have a little bit more functionality in that if multiple processes have signaled that the resource is available, S will be greater than 0, maybe greater than 1, right? It'll be a value. Let's say it's 5. Okay? Well, let's say S is 5. If I come in to wait and I see S less than or equal to 0. What is S? Is that less than or equal to 0? No. So what does that mean? Do not wait. So what do we do instead? Go to the next one. Subtract 1 and move out. So in other words, the wait call would return, and we've decremented the semaphore. Right? Another process comes in. What's the S now? It's 4. 4 will go through. 3 will go through. 2 will go through. 1 will go through. Now it's 0. We'll loop. We'll stay in here until somebody comes back and signals. Who will signal? Somebody who already took the semaphore.
I think I missed the very beginning, like, the processes are each doing waiting and signaling.
Yes. So the idea is this. Waiting for a semaphore is acquiring a lock. Think of a semaphore as a bucket of tickets, right? How many tickets are in the bucket is the initial value of the semaphore. Okay? If it's 1, it just acts as one can use it, then puts it back in, and then another can use it, puts it back in, type of thing. Okay? If there's more than 1, you could have 5 tickets, and 5 people could get a ticket and go do something and then come back. So the idea of waiting is you wait, get a ticket, go, and then when you're done, signal is putting the ticket back in the bucket. Okay? So it's kind of like what we did before. Before we were locking. When it's our turn, we go, and then we set ourselves as unlocked. In other words, anybody whose other turn it is can go now. Right? So that was kind of one or the other. Here we've made it more complex in that we say 5 people can go at once. But none of you can go until one of those 5 people is done and puts their ticket back. Okay? This already opens the door to a whole bunch of problems, right? What's one of the big problems that can happen?
You get stuck. No one returns ticket.
Okay, so one of the big problems is you don't return your ticket, whether it's because you get stuck or what? Or you just walk away with it, right? You just never call you never call signal. Okay? That's an error in your program. Okay? Now, it is possible that even though you have a semaphore, outside of that, you still may be able to kill the thread or something like that. Okay? This is to regulate normal operation and accessing things. So, using these semaphores, our goal is not to regulate how you access the semaphore. Okay? Hopefully, the operating system will provide a good signal and wait that we know works. Okay? Our goal is to have the semaphore represent your access to other useful things, like a counter variable in a producer-consumer problem. Okay? That counter variable, we don't have atomic operations that can work with it. So what we need to do is we need to wrap it in some of these things. So what we might say is, here's a semaphore associated with that. So in other words, unless I have the semaphore ticket, I will not manipulate counter. If you say that and you write your code like that, you've made it so that you can get a semaphore, manipulate counter, in other words, do your critical section, and then you give the ticket back because you're not going to manipulate counter anymore. Does that make sense? Okay? Because we've been seeing these snippets of code where there's a locking, critical section, and then an unlocking. In good multi-threaded, multi-process code, you'll be doing this all the time. Locking something, accessing something, unlocking it. Because, what have we already said? The longer the section of code that you lock, what does that mean to other processes? They have to wait if they want to access any of those things you've locked for. Right? Because we're not locking the CPU, we're not locking the time slices that other processes are getting. We're locking access to variables that we share, maybe input-output devices that we share. We're locking access to resources. Okay? So, if we need to access a resource and something's going to come along and lock for it, the bigger the section of code that we lock, the more chances that somebody's going to get to a point where they need that resource and they have to wait. So, semaphore. Everybody see the difference between this semaphore and just our simple lock, unlock. Okay? That lock, unlock mechanism, that simple, I'm going, no one else can go. When somebody else wants to go, I'll have to unlock, and then they can go. You usually see that referred to as a mutex. M-U-T-E-X. Okay? A mutex stands for mutual exclusion. Okay? Remember when we were doing it, it was really, what we were trying to do was, if I'm using it, no one else can use it. Mutual exclusion. Okay? That's really a simple version of this, okay, of the semaphore. It's just one person at a time. This is, I have tickets. If I have tickets, you can come through. If not, you have to wait. Just return your ticket when you're done. Okay? Two simple operations. Really good, because then the operating system can provide these two operations, and now you have a very powerful synchronization object that you can work with. So then you can expand this into more complicated things. Okay? Counting semaphore, this idea of the fact that it can increment, you can use it to keep track of, how many threads are done and that kind of thing. A binary semaphore, oh, here we go. A semaphore that can only be 0 or 1 is this, right? A mutex lock, and that's the simple thing that we saw initially. Okay? You can implement a counting semaphore as a binary semaphore. What does that mean?
I have two values.
What's that?
I have two values.
Okay, but how could I implement more than 2 values if all I have are binary semaphores?
Like,
Use several of them.
row.
Just count in binary, right? Each one is a digit. So you just keep adding more semaphores. Okay? Actually, just for your information, that's an actual more high-level theoretical computer science proof, is that most algorithms and things, if you can prove that an algorithm is correct or works with 0 and 1, it generally works. Which is neat. Okay? You see it in like architecture and things. If you build a single bit adder, you can create any arbitrary adder at that point, right? By chaining them together. Okay? First statement, must guarantee no two processes can execute wait and signal on the same semaphore at the same time. What is that known as? No. There's a single word. Signal and wait are atomic, right? Signal and wait are atomic. Okay? Becomes critical section problem, wait and signal are placed in the critical section. Okay, again, we solve the basic critical section problem, then we can provide things like semaphores. We provide things like semaphores, we can do fancier things with our synchronization. Okay. Well, we're going to spill over into the next class. This is a hard chapter, so I don't mind spilling over. One thing that is interesting about semaphores is this idea of semaphores can be implemented so that they do not spin. Okay, how do you do that? Well, remember, we've already seen this kind of waiting problem before, right? Like with things like hardware and things. If I want to go to disk, what does an operating system usually do? Well, I say, okay, I wanna get this value. I want to get this data from disk. I'm a process. So I go and I say, hey, operating system, I want to get this value from disk. What will it do with me? Put me on a wait queue, right? So I'm not eligible to run anymore. In other words, I am quietly waiting for what?
Get the IO.
Okay, so the IO comes back. So does that mean I start running?
Not ready.
Does that mean I go into the ready queue? An interrupt has to happen from that coming back, from that data coming back. Interrupt has to happen so that I will be moved back to ready queue so I can run. Same idea here, okay? What they'll do is when you go to use the semaphore, okay, if the semaphore is not ready for you, you sleep. In other words, you sleep and then the operating system will wake you up when the semaphore becomes available. So think of the semaphore as this disk I/O or whatever it is we were waiting for before. It's the same idea. You'll wait quietly. What's nice about you waiting quietly? Well, you don't get scheduled to go on the CPU because we know what you're doing, right? You're waiting for that semaphore to be available. So in other words, instead of spinning in a while loop, you sleep. And we won't come back to you until the semaphore becomes available. When the semaphore comes available, operating system wakes you up, and puts you on. It's up to the operating system how it sleeps you, whether it puts you on a queue, if the queue is first come, first serve, that kind of thing. Okay? That's what's nice about these semaphores is the program just sees wait and signal. But how you implement it in the operating system, right? These are system calls. How you implement it is up to the operating system designer. So, yeah?
Would that help you, like, is that how operating system would be like rewritten? Solid code?
Yes. Oh, I mean, is this simple? Maybe, maybe not. With primitives like this, it could be that few lines of code. But you'd also need to do things like turning off interrupts, turning them back on so this is done safely. And whether this would probably get down to assembly and some, I don't know. But yeah, I mean, for the most part, yes. And then also, the other thing is that this might be conditional as to whether or not you're uniprocessor or multiprocessor. Because, for example, in multiprocessor, you'd go back to the old implementation, right, with the spin. Okay? What you'll find is that most things in multiprocessor use spin locks, whereas uniprocessor can use interrupts turn off. Okay? But yeah, who knows? Who knows if there's more complex code that needs to be in there for a full-blown operating system. But even if there is, chances are it'll get down to there being some primitive like this. That's as simple as this. Okay? That's a good stopping point. We'll talk about deadlock and starvation, which are the two major problems in synchronization next time.